Okay, I thought I would back us up a little bit and give us a little bit more practice with making our alkynes. So here we have two different dihalides. The top one is an example of a geminal dihalide, and the bottom one is, of course, a vicinal because they're on two different carbons, two neighboring carbons. One of the sets of reagents that we really emphasized for this semester was using sodium amide. And if we look at our 1-pentyne structure, we can see that it is in fact a terminal pentyne that would have been, or a terminal alkyne that would have been hinted at from the 1. So if we use XS, so XS is how we abbreviate that in our reagents, sodium amide, we're going to want to also use water to eventually protonate our alkylide anion that will generate by doing this double elimination and eventually a deprotonation step. So that's one of the possible reagents. So down below, we can think about some other reagents that we could use. We know that these are just eliminations, doing 2 eliminations, so we can use other bases besides sodium amide. A good base that would be possible and especially synthetically useful for this vicinal diol would be to use our tert butoxide. Okay, so here I am drawing it out, but of course we could have also written it TBUOK. That's maybe how you've been practicing it. The tert butoxide is a strong base. We could have used some of our other strong bases, but the tert butoxide is a bulky base. And so we know that that's going to really emphasize doing the elimination between these 2 carbons on the end instead of potentially creating an extra 2 double bonds that are accumulated the way that we discussed in class previously. So the bulky base is the best choice when trying to make this terminal alkyne. All right, so here's another set of reagents. We'd practiced and at least discussed making our alkynes into alkenes. Here we see a cis 2-pentene in the top example. And so things that you can immediately think about is, okay, I have a specific geometry. Here's my 2 hydrogens, so we are using that cis nomenclature here. Of course, it could also have been Z2-pentene as Klein starts to use more and more. And the way that we create these cis alkenes is to use hydrogen and then some kind of poison catalyst, maybe a Lindlar's catalyst. And really, you could have just written poison catalyst. We talked about a couple of them, but Lindlar's was really the most popular one. Down below, we have a trans 2-pentene or an E2-pentene. So we had discussed ways to make our alkene stop in this transformation, and that was the dissolving metal reduction. So you had sodium metal and liquid ammonia. And so that would be how you would solve for this one. So these are examples of the short answer problems that I might give you on the test where you're having to fill in reagents. So next up, this is starting to get into some of the new material you were supposed to look over yourself. The top one is creating an enol. So here's our alcohol, here's our double bond right there. So hence enol, right? And right before I left for the conference, we talked about a certain reagent that will make this enol. And if we look at our double bond, so here's the R group, here's the R group, so that means this carbon is this carbon. Okay, and here's a hydrogen. And so here's where we now have 2 hydrogens on that alkene. So this is following Markovnikov's addition. And in order to do that, we have this mercury catalyzed hydration reaction that we can do with our basically our acidic solutions. Okay, so we see HgSO4 being used as a catalyst. It's still following Markovnikov's rules and adding the alcohol onto the more substituted side. And this enol, we know we can see it tautomerize into the ketone, okay? So here now, in the bottom example, we have a proton on the end of that alkene, so perhaps it's the same alkene, it's an R group, but now our alcohol is adding to the less substituted side. Okay, so it's anti-Markovnikov addition, so it's going to be a variation of the hydroboration oxidation reaction that we saw in chapter 8. So we're still going to be using some kind of boron to begin with, but if you read in the book and in your slides, you see that we're not just using BH3 with THF anymore. We're using 9BBN, which is effectively a bulky borane, to ensure that we're not getting a mess of products. That's the main thing. So we're seeing these bulky boranes to be used when we have our alkynes that we're trying to do these hydration reactions with. So that's step 1. Step 2 is the same as it is for your alkenes, so peroxide and base, in order to create our enol. And this time, because our enol is on the outside, so the alcohol is on the terminal position, the end of the molecule, we see the tautomerization resulting in the creation of an aldehyde instead of creating a ketone. Okay, so ultimately, the way that this is happening, and I will back out of this really quickly. We'll add in another slide. So that we can see what this mechanism looks like. Okay, so we have our enol. Okay, so it looked like this on the slide before, so I'll try to give us some consistency with how it's drawn. Okay, and now we have a base catalyzed reaction because step 2 is involving the base. This was done differently with our acid catalyzed hydration. And we will continue to see this mirroring of an acid mechanism followed by a base mechanism. The acid mechanism typically has a protonation step first. The base mechanisms will often have a deprotonation step. And so that's exactly what we see here. We see our base from that sodium hydroxide come in and deprotonate the alcohol in the enol. And of course that will leave behind our double bond, or that will leave behind our oxygen with a negative charge in the lone pair, okay? All right, so now we have this situation that is one of our resonance patterns, right? So we know that we can move the electrons on the oxygen down to form a carbonyl, and that will push the electrons that are part of the pi bond onto that sp2 hybridized carbon. So now we have the structure looking like this with a lone pair on this carbon right here, okay? And so if we remember, it's a basic solution, so bases are always dissolved in water, and so we have our water molecule floating around here. This is a very strong base. It will deprotonate that water, regenerating our hydroxide and leaving us with the aldehyde product that we saw the slide before right here. Okay. So this is an example of a multiple choice question that we could see. And this is one where it's asking you which ones give you ketones and which one gives you aldehydes. So if we were doing this on a test, I would probably just ask you to give me one for a multiple choice. And of course they would have like A, B, C, D's for your different options. But for ketones, we're looking for a Markovnikov addition. We want that OH to add on the inside of the alkyne, okay? So we're looking for Markovnikov here. And then for aldehydes, we're looking for anti-Markovnikov because we want our oxygen to end up on the last carbon in what used to be the alkyne so that we can make the aldehyde, okay? So I'll add anti-mark to this so that we don't get confused with syn and anti-addition that we talked about last chapter. All right, so A, we have a terminal alkyne, and this is that acid catalyzed. So A is going to make a ketone, okay? So is D, okay? And if we keep looking, we're going to see the rest of these are hydroboration oxidations. So traditionally, they would give you anti-Markovnikov addition. So if we look at B, that's a terminal alkyne, and so our alcohol will be adding to the outside. So B will create an aldehyde, okay? E is also a terminal alkyne, and so it will also give us an aldehyde. But C and F are internal alkynes. And so there isn't a more substituted side because it's an alkyne and there's only one group coming off of each. So in fact, even though C and F reaction conditions are anti-Markovnikov, we're not seeing an aldehyde getting formed because this isn't a terminal alkyne in the first place. And yes, I noticed that here and here for B and C we have BH3 THF. Really, that should be 9BBN for the most efficient reaction. And this disamal borane for E and F. That's one of the other bulky boranes that we talked about, or that you saw in the slides. 9BBN tends to be the favored reagent of Klein, and I think, again, that's because of the efficiency of writing that reagent out versus writing out disamal borane every time. Okay, so this is one of those open-ended questions, so effectively on the test, instead of having a question mark, I could just have a box here and ask you to give me what the product should be, okay? So ultimately, hopefully you can recognize that this is a terminal alkyne, and this is that acid-catalyzed hydration reaction. So we should be making some kind of ketone. Obviously, that's not a good enough answer for the test. We need to draw the whole structure. So if we're numbering 1, 2, 3, 4, 5, 6, 7 carbons, so I'm going to need to draw 7 carbons for my final product. There's 2, 3, 4, 5, 6, 7. Okay, so my alkyne was between 1 and 2. So my ketone is going to go there on what is the 2 carbon. Okay. So if we wanted to kind of look at this again, because I know we did this towards the end of class when we were calling what the material was for our exam, ultimately an intermediate in this is our enol that's on the more substituted side of that alkyne, okay? So if we draw the mechanism, we have our acid, because this was an acid-catalyzed reaction, right? And the tautomerization is initiated by this acid existing. We see the pi bond seeking out a proton. This should be positively charged. And that will go and add in a Markovnikov fashion. So now we have gone away from the sp2 hybridized carbons, and we have created a carbocation. Once again, we have a resonance pattern, so the lone pair on the oxygen can go to fix our formal charge on the carbon, the carbonyl carbon, and so I'm still going to draw in these hydrogens just for our purposes. You would not have to draw these on a test. We end up with this scenario here where we have a positive charge on the oxygen. This is the more contributing resonance structure because all of the octets are met. And we, of course, just generated water. So our water molecule can come back here, or a different one can come back. It can deprotonate the proton, moving electrons onto the oxygen in the carbonyl, and that would give us our ketone final product for this guy. So I'm going to put an R here, go back in and put in all of my R's, because this is in reality this very long chain that we have in this heptyne as the starting material. Okay, so this one should actually have step 1 and step 2 because it's a hydroboration oxidation reaction. Literally, I've got the diethyl borane boron reagent here, so there's our reminder. Instead of seeing the B like in the 9-BBM or the BH3-THF. So hopefully we can remember that this is anti-Markovnikov, and so our OH adds here. Okay, and so our final product is going to be, in fact, an aldehyde instead of a ketone. And so we see, I think this is going to be a heptyne again, but let's count 1, 2, 3, 4, 5, 6, 7. Yes, it's a heptyne. So we're basically just using 2 different sets of reagents. So 1, 2, 3, 4, 5, 6, 7. And on our 7th carbon is where the oxygen is going to be. And then you can draw in the hydrogen. You may have also seen your aldehydes drawn like this because they're bond line structures. This hydrogen is also assumed, so you don't have to draw that in necessarily. Okay, so here we're seeing another one of the new reactions you were supposed to read about on Friday. This is basically our halogenation reaction for our alkynes. And typically when we do these, we see excess of our halogen used because that's the most synthetically useful. If you're only using one equivalence of your halogen, you may get a mixture of products, some that have 2 halogens added across the triple bond, and some of them may have 4 halogens added, some of them may have not reacted at all. So it's best to always plan to do these with excess. We don't know the mechanism, so this isn't one that you necessarily need on the test. But what we'll see ultimately is 4 bromines adding across this triple bond. And I'm counting here to see how many, and that's what I thought. It's another heptyne. So now I'm going to draw out my carbon backbone. So 1, 2, 3, 4, 5, 6. Here's 7. And my bromines are going to add to the 1 and the 2 position. Okay, and the excess ensures that it's getting used. Carbon tetrachloride, we've talked about this before. It's just a good solvent. For these halogenation reactions, it's a non-polar organic solvent, and so it ensures that it dissolves our hydrocarbons, okay, so our alkynes really well. Okay, an example of a multiple choice question. So this is ozonolysis. The O3 is hopefully the big hint here. And you read about how there's a difference in the products you make for ozonolysis of an alkyne versus an alkene. Alkenes, we were just putting a carbonyl where the sp2 hybridized carbons used to be bonded to each other. We're still cleaving these pi bonds, and in fact the sigma bonds, but now there's enough oxygen around that we're going to put oxygens on, attach those carbons to as many oxygens as possible. So here we have a terminal alkyne. That means that one of our products is going to be CO2 because carbon can have 4 bonds to oxygen in the form of this gas, and we only have 1 carbon here, right? then that leaves 1, 2, 3, 4, 5, 6 carbons for our other structure. That other structure is going to become a carboxylic acid. So that takes 3 out of the running because this actually has 2 carbons in it. Okay, so that would have had to have been from an internal alkyne. And I think 1 has the right number of carbons. Yes, that would appear to be the case here. 5, 6, 7. So 2 has too many, okay, because we're losing one of our carbons to one of our products, the CO2. And so our other product is going to be 1. So the correct answer here would be D, 1 and 4. And if you count them up together, you end up with 6 plus 1, 7 total carbons for the reagents. And if you were to count over here, you have 6 plus 1 when you count up your total number of carbons in the original alkyne. So, here we see one of the most important reactions that we get out of this chapter. This is a 2-step reaction using the alkyne anion that we saw earlier. So the sodium amide is going to deprotonate this terminal alkyne. So this is actually going to become, and I'll go ahead and draw this out. I think this is another 4, 5. Oh, actually it's a 6. So this is going to become this guy after step 1. Okay, so this is a very good nucleophile. We have the lone pair on the carbon. It's a carbanion. And now pentyl chloride, here we are using a common name. So we have to remember what that looks like. There's our pent group. There's the chloride. Pardon. And so this is a primary alkyl halide that we're going to see undergo SN2 reaction mechanism with this good nucleophile. Okay, so what we should be looking for is an alkyne that's in the middle, and it has 6 carbons on either side of that bond. Or rather, it's going to have 5 carbons on one side and 6 carbons on the other, because we're going to have 1, 2, 3, 4, 5, and then this will start off our 1, and then we'll have 2, 3, 4, 5, 6 after the substitution reaction. So we've got, this is actually 1, 2, 3, 4, 5 carbons. And here we see 1, 2, 3, 4, 5. Okay, so that's the metric. A doesn't work. Okay, D does not work because we don't have anything that would do a hydrogenation all the way down to an alkane. C also doesn't work because we don't have the dissolving metal reduction to do to create our transalkene. That leaves us with B. Let's just count to double check. Here's carbon 1, 2, 3, 4, 5, and 1, 2, 3, 4, 5, 6. So yes, B would be the right answer. And of course we wouldn't number that way for nomenclature purposes, but it's an easy way to count to make sure that we've accounted for all of the carbons in our 2 reagents for our alkynide reactions. And ultimately, this reaction is super important because it's the only way we've learned so far to really grow our carbon chains by anything more than 1 carbon. We know that cyanide is a good anion, this guy right here, our cyanide anion, but that's only growing the chain by 1 carbon. And so it's not allowing us to really build larger and larger molecules. Okay, so this is going to be an example of a multi-step synthesis we have an alkene, okay, and it has 1, 2, 3, 4 carbons in it. We're making a ketone, which we now know how to make. We have a reaction that will do that. And we have 1, 2, 3, 4, 5, 6 carbons. So one of the things that Klein taught you towards the end of the chapter is always look for chain growth, so your carbon chain growth. And then as you're looking at your multi-step synthesis, you look for functional groups, okay? So number of carbons is the first thing you check for, and then functional groups. So we definitely are changing our functional group. It's going from a ketone, from an alkene to a ketone. If we count, okay, we've got starting at our ketone, we have 1 carbon, 2 carbons, 3 carbons, 4. Okay, so that kind of mimics what we have in our starting material. So maybe we're not moving the location of the functional group. We're just changing what the functional group is. So if we have 4 carbons accounted for here, okay, that means we are adding in 2 more. Okay, so the first thing we're going to need to do, we need to grow this carbon chain. We don't have an alkyne to grow the carbon chain yet, so we're going to need to do an addition reaction in order to generate a molecule that can yield an alkyne. So my first step is going to be Br2, doing a halogenation. So we could include our solvent, the carbon tetrachloride, if we wanted to. So that's going to give us this guy about like that, okay? So it's giving us our bisatyl dihalide, and we know that we can be really careful with this if we want to and use TB, okay, so that terp butoxide in order to make, and I'm going to start with our triple bond so I don't mess up my bond angles, 1, 2, 3, 4, okay? So we have our alkyne now, okay? Let's put in excess terp butoxide. I don't really think that's very necessary because terp butoxide would be an aqueous solution and would be in excess anyways. Okay, so now we need to introduce something to deprotonate that proton to make our carbanion, our alkylonide anion. So step 1 is going to be sodium amide. Okay, so that's going to give us the carbanion. Step 2, this is an SN2 mechanism, so it always preferentially will be a primary alkyl halide. If you're in a scenario where you're trying to build a structure and you have one side that's bulkier, that's usually going to come from the alkyne side because this needs that capability for a backside attack. So here we've got 2 carbons, and let's make this be, for instance, an iodine, so a really nice leaving group, and that will in fact take this structure to this, okay? All right, so that's great, but also not the final product yet. So we're starting to see how we have all of these reactions from several chapters building up. Truly a nice multi-step synthesis. We are trying to make a ketone. This is an internal alkyne, so we could use either acid catalyzed hydration or hydroboration oxidation. They're both going to yield a ketone since it's not a terminal group. I'm going to go ahead and do our acid catalyzed, so we're going to have that sulfuric acid and water and HgSO4 as our catalyst in order to create, and now we know it's going to make the enol, but it will tautomerize into the ketone, and so we don't really need to draw out this whole structure. I'm just going to number one more time on our alkyne to make sure that I did the right, that I'm drawing the right structure. So yes, we've got 6 carbons, and so ultimately we will see from our purposes, there's 5, here's 6, and we had, if this is numbering 1, 2, 3, 4, 5, 6, so the alkyne was between the 4 and the 3, and we could feasibly create the enol on the 4th carbon, the way that I was numbering it. I know that was not numbering correctly for IUPAC, but we could do the addition on the 4th, on this carbon that we see that I just put the arrow on, and that would create eventually the ketone functional group. Okay, so this is an example of a multi-step synthesis asked in a multiple choice question. So it's a word problem, truly. And you will see practice problems like this in the book and in the problem packet. And this is a classic organic multi-step synthesis question now that we've got alkyne chemistry underneath our belts. So starting with acetylene, so the simplest of our alkynes, and this is where nomenclature is getting tested on your multi-step, because if you don't know nomenclature, you don't know what your starting material is. Starting with acetylene, what would be the appropriate set of reagents to produce 2-methyl-4-nonine? All right, so nonine is going to be a 9-carbon alkyne, and I'm going to draw it with the wrong geometry to begin with, okay? So 1, 2, 3, 4, 5, 6, 7, 8, 9, okay? So 1, 2, 3, 4. Okay, so there's our molecule. This is bad, right, for the bond angles. So we will fix it, and usually when I'm doing that, I will start with my triple bond in the middle. Okay, so here's this carbon right there, and we're going to have our lines coming straight out from that with the proper geometry. So this is this carbon right here, and now our geometries can go accordingly. So here we see our 2 group, okay, and now I've got this carbon here represented over there, and we go to 1, 2, 3, 4, so we're at 1, 2, 3, 4. Okay, so if we count all this up, 1, 2, 3, 4, 5, 6, 7, 8, 9. All right, so there's our 2-methyl-4-nonine. Very obviously, if this is our starting material, the acetylene, then we have to grow our carbon chain. If you remember what you read from these very powerful SN2 reactions, so really the only thing that was new about these alkyne anions, it was just a new nucleophile, right? Mechanistically, this was something that you already knew how to do. We just hadn't looked at using our anions this way. So, your book is calling it the alkylation of terminal alkynes, because ultimately we're adding on alkyl chains on either side of the triple bond. But what the slides emphasized and the book emphasizes as well is that this has to be one step at a time. So you should never try to deprotonate both of your hydrogens at the same time and add on, because you're going to get a mess of products. And typically you're not doing this and trying to create a symmetric alkyne. You want to make something interesting like what we're doing today, the 2-methyl-4-nonine. So the fact that it's a nonine does tell us that we're done with the reaction. We're not trying to really, or we can design it so that we don't have to do anything after we do this alkylation reaction, okay? So ultimately, we want to add So let me go and redraw this on a new slide. Yeah, if we can. Okay, so here's this guy. So this is 4, 5, 6, 7, 8, 9. And we're wondering what we need to do from this. Okay, so if we're counting from our alkyne, we need to add 1, 2, 3 carbons with a branch point, and 1, 2, 3, 4 carbons. So that's 7 plus our 2 from the original acetylene. That does make 9. So I drew my structures correctly. Okay, so that means step by step, we're going to need to effectively, we can kind of picture cutting this out and having 1, 2, 3, 4, some kind of halogen here, and then also having, I actually drew that wrong, some kind of halogen, not here, but instead it will need to be here. Now, what did I do wrong here? I paused and said, oh, I did something wrong. If we look, I drew my shape correctly, and this is actually a common mistake that lots of people make when we're doing these reactions. And then I put my X here, but that means that this is not a carbon anymore. So in reality, I'm only adding 3 carbons, and I need to add a 4th carbon. So be careful when you're kind of picking apart your molecule that you don't shortchange yourself carbon-wise. You may draw your reagent wrong and draw your final product right, but that's when you're kind of magicking up matter and adding in extra carbons. So this is actually what our 2 halogens should look like. They are, in fact, both primary halogens, so they should do very well with an SN2 mechanism. So now we need to just look back at our answer possibilities and see what order of reagents works with these. It doesn't matter which one we add first. They just need to be added in a stepwise formation. So each one of these we see starts out with sodium amide. So that's great. It's going to deprotonate one side of that acetylene. And notice it's just one equivalency because we were purposefully only deprotonating one of the protons and creating this nucleophile, right? Okay, as I'm looking through these, I see several options that go NaNH2, alkyl halide, NaNH2. That's the pattern we're looking for the stepwise mechanism. So that means we can eliminate C because it's adding the sodium amide and then it's back to back adding the 2 halogens. That's not going to work, right? We're going to need to eventually deprotonate the other halogen, the other proton, but that's only capable and should only be done after you have added in a new R group, okay? So that gets rid of C, that actually gets rid of D, and that also gets rid of E because E is using a base, but it's not a strong enough base. It's your ethoxide. So now all we have to do is look at our halogens, and this is nomenclature. So, and this is a really great ACS style question because you have to know what your nomenclature is. So 2 of them are using N-bromobutane. The N means normal. So a normal alkyl halide has the halogen at the end. No branching is another way to think about it. So 1, 2, 3, 4, right? 3, 4. So this is N-bromobutane. Flip back. Looks exactly like this guy, right? Okay, so N-bromobutane is good. We also kind of knew that, but I wanted to talk that through with you since this is our first time seeing it. Now, the big difference is the number 4 reagent, tert-butyl bromide or isobutyl bromide. Okay, let's go back to my working slide. So, tert-butyl bromide would look like this, or really it would have that be a BR, right? So that would be a tertiary alkyl halide, no-go for SN2, right? Like, that would not work. This is isobutyl, an isobutyl halide. Okay, so in fact, isobutyl bromide looks like this, and so it still has the 4 carbons, they're just branched differently. And if you aren't comfortable with your common nomenclature, you might not be able to tell what isobutyl bromide is. You might be able to still get the right answer, which hopefully we all recognize as B at this point, because that tert-butyl group is something we've used a lot with our bulky bases. Okay, that's all of the practice problems from that I had set up for us to review after looking through the rest of the slides from chapter